We've talked about the inversion symmetry of individual orbitals for diatomic molecules, and now we want to talk about what that implies for the inversion symmetry of the total wave function. So I've got here several types of orbitals which are common in diatomics for the types of first and second row atoms that we looked at. So sigma G are sigma orbitals that are symmetric with respect to inversion, inversion being going to the opposite point relative to the center of this internuclear axis here. So going from here to here, positive to positive, positive to positive, positive to positive, that's Gerada, because inverting gives you the same sign in the wave function. The sigma antibonding orbitals, sigma star, are ungerada, or U, because going through the inversion center always switches the sign of your wave function. And similar thing with pi bonding orbitals, you go from positive to negative, positive to negative, positive to negative anytime you invert through that center there. And same thing with the antibonding orbitals for pi bonds. You have pi star G, they are Gerada because you go from positive to positive, negative to negative, negative to negative, 0 to 0, etc. So those are symmetric, they are Gerada. And this comes from the inversion operator, which commutes with the Hamiltonian, and so we have this inversion operator acting on our wave function gives a constant times the wave function again, and this constant can be plus or minus 1, and that determines whether this is Gerada or ungerada for these individual states here. But these are the four most common states, so this will pretty much be the case for anything we're worried about. So the question now becomes, given that this is the state of individual spatial orbitals and individual spin orbitals, what does this imply about the inversion symmetry of our total molecule? So in order to look at that, we need to define some rules. So our wave function is going to be a product of individual orbitals, individual spin orbitals. So we're actually multiplying the symmetries of these orbitals together to get our total symmetry. So if we have something that's symmetric times something that's symmetric, this is essentially equivalent to an even function times an even function. So that gives us even back, that gives us symmetric back. G times G equals G. If we have something that's symmetric times something that's antisymmetric, that's also equivalent to something that's ungerada times something that's gerada, and that gives us the total result of gerada. So that's very analogous to even times odd equals odd times even equals odd. And just like even and odd functions, ungerada times ungerada, odd times odd equals even. So using these rules here, we can actually get what the total inversion symmetry of our wave function is based off of the electron configuration and what individual spin orbitals our electrons occupy. So if our total wave function is just, for example, we have one sigma G1, one electron in a sigma G orbital, then it's obviously the total wave function is Gerada. If we have one electron and it's in a sigma star U orbital, then that's obviously ungerada. If we have two electrons in a sigma G orbital, that's G times G, that gives us Gerada. And if we have two electrons in a sigma U orbital, then that's U times U, and that total result is Gerada. So the result that's going to happen because of this is anytime we have a fully closed shell, anytime we have two electrons in every spatial orbital like this, we're always going to get a completely symmetric wave function, a Gerada wave function here. So it's really cases where there's an odd number of electrons where we're going to get the more interesting cases where you have the possibility of being either G or U. So we have cases like, let's say we have helium-2 plus. So it's helium with 3 electrons. So that configuration would be 1 sigma G2, 1 sigma star U, 1. So the total symmetry of this wave function would be G times U. G times G is G, and then the resulting G times U is U. So a helium-2 plus would be ungerada in its symmetry. If we have H2 plus, the hydrogen molecule with 1 electron, then that's just going to be one electron in the sigma g orbital, the lowest energy orbital. That's 1 sigma g1. So that total, as we saw here, is just going to be Gerada. Then we have cases like, let's look at boron 2. That configuration has 10 electrons, so according to our diagram from a couple videos ago, that's 1 sigma g2, 1 sigma u star 2, 2 sigma g2, 2 sigma u star 2. Then our final 2 electrons are going to be 1 pi u 2. So the total result of this, G times G is G, U times U is still G, so still G, times G times G times U times U. And then the final orbitals here, we have U times U. So in each case, we have all of our orbitals have 2 electrons in there. So the final result of G times U, U, G, G, U, U, times U times U. If you work that out, total result, that ends up becoming G as well. And then let's look at another case which is of a similar configuration to the types of term symbols that we discussed in the previous video. And that would be a case where we have just, let's say we have 3 electrons in some type of pi orbital there. So let's look at F2, let's say F2 plus. So that would be 1 sigma G2, 1 sigma U star 2, 2 sigma G2, 2 sigma U star 2. Okay, we're up to 8 electrons. And we have 3 sigma G2, 1 pi U 4. And then we're up to 2, 4, 6, 8, 10, 14 electrons. So we're going to have 17 total because we have 18 from fluorine, then we take away 1. So we have 1 pi star G 3. So the final result was that we had 3 electrons in that pi G orbital at our frontier. All of these orbitals are doubly occupied or fully occupied in their subshell, so they're going to give us a G for the total. Then at the end we have 3 electrons, an odd number of electrons in this pi star G orbital. So those are all going to be times G. So the total result we end up getting there is G. Gerada for the total case. Now this is useful because the symmetry with respect to inversion of the total wave function can be something that we append to our molecular term symbols to give a little bit more information about what that total wave function looks like as well. So using the types of term symbols that we showed from the previous video, H2, which would just be this case right here where we have 1 sigma G2, that we said was Gerada, and for H2 the ground state term symbol was a singlet sigma. So the term symbol can actually use the inversion symmetry on the bottom right here. So we would say that H2 has a ground state term symbol of singlet sigma G. Okay, then we looked at also something like He2 plus, where we had 1 electron in a sigma star U orbital, and that total wave function symmetry was U, and the term symbol we had for that was a doublet sigma. So for helium-2 plus, we could have a term symbol of doublet sigma U for the ground state. Then the example we looked at for boron-2, which is 2 electrons in 2 degenerate pi orbitals. For boron-2, the types of term symbols we got there, in each case this is going to end up being Gerada. So we had singlet delta G, we had triplet sigma G, and we'd have singlet sigma G. Then for F2 plus, which is the other case we looked at where we had 3 electrons in some 2 degenerate pi orbitals there, like these pi star G orbitals, these 2 spatial orbitals which make those up. So for F2 plus, our ground state term symbol would have been a doublet pi g. So this is the completion of molecular term symbols, looking at what they look like. So they not only have this superscript of 2s plus 1 and then the Greek letter indicating their value of the absolute value of m sub l, we also append on this label here about whether the total wave function is Gerada or Ungerada, symmetric or anti-symmetric with respect to this inversion operator.